Chrome fixed 1,072 security bugs in June 2026. That's more than the previous 23 releases combined. Chrome 1, 49, and 150 shipped in June. Together, they crushed a 2-year baseline, 1,036 bugs across 23 prior releases. The spike wasn't human, it was ClusterFuzz, Google's 100,000 VM fuzzing cluster, now turbocharged with a Gemini-based agent. Here's the problem. Traditional fuzzing throws random input at a binary. It finds shallow bugs fast, but deep logic errors hide behind narrow entry points that random bytes never reach. And it gets worse. By March 2026, Chrome received more bug reports in 1 month than in all of 2025. The system drowned in crashes. The bottleneck shifted from finding bugs to processing them. So let's take it apart. ClusterFuzz runs 3 engines in Ensemble: libFuzzer for structure-aware fuzzing, AFL++ for coverage-guided mutation, and Honggfuzz for hardware feedback. They share one global corpus. Every fuzz target is declared in a GN build file. The fuzzer test template auto-wires the seed corpus, the dictionary for mutation hints, and sanitizer flags for memory safety checks. ClusterFuzz uploads every crash corpus to a GCS bucket. Each target gets its own namespace, versioned by commit. The corpus persists across runs, so new fuzzers start from every crash the cluster ever found. Here's a typical fuzz target. It takes raw bytes from the fuzzer, wraps them in a string view, and feeds them to the URL parser. If the parser crashes, the sanitizer catches it, and ClusterFuzz files the bug. libFuzzer uses sanitizers to detect bugs at runtime. Address sanitizer catches out-of-bounds access and use after free. Memory sanitizer catches uninitialized reads. Undefined behavior sanitizer catches signed integer overflow and null pointer dereference. The sanitizers instrument every allocation, every pointer access, every operation. Each fuzzer runs continuously. It mutates the seed corpus, flipping bits, splicing inputs, inserting constants from the dictionary. When a mutation discovers a new code path, that input joins the corpus. The next mutation builds on it. Coverage grows incrementally, generation by generation. The mutation strategy is not naive. libFuzzer tracks edge coverage, not just which functions ran, but which control flow branches executed. It prioritizes inputs that unlock new edges. When it discovers a previously unreached comparison, it performs targeted bit flips around that offset to satisfy the condition. This feedback loop is how shallow random mutation gradually reaches deep code paths over millions of iterations. In early 2026, Google wired a Gemini-based agent into the harness. The LLM reads the target source code, the API documentation, and past corpus files, then generates structured test cases that exercise narrow code paths random mutation never hits. Traditional fuzzers mutate raw bytes. The agent outputs valid C++ that calls the API correctly. Hitting branches, random input never reaches. Here's what the agent generated for the URL parser. The agent doesn't just write one test, it generates dozens, each targeting a different branch condition. Port parsing, query string decoding, fragment handling, IPv6 literal parsing. Each test is a valid program that compiles and runs. No garbage bytes, no invalid state. Traditional fuzzing measures code coverage and blocks hit. The agent targets semantic coverage, authentication flows, error paths, edge cases that appear only under specific preconditions. It reasons about what the code does, not just which lines run. Here's the mechanism. The agent receives the fuzz target source, the header files it includes, and a sample of existing corpus entries that triggered high coverage. It builds a mental model of valid input structure, URL syntax, HTTP semantics, encoding rules. Then it writes tests that satisfy constraints the parser expects. Well-formed port numbers, valid percent encoding, correctly bracketed IPv6 addresses. These aren't random bytes that happen to parse. They're intentionally crafted calls. The numbers tell the story. Before the agent, Chrome averaged 45 bugs per release. After the agent landed, June's 2 releases hit 536 bugs each. The gap collapsed overnight. Big Sleep, the collaboration between Project Zero and DeepMind, uses a similar architecture, but Google won't disclose its details. The Gemini agent in ClusterFuzz is the only one we can trace. ClusterFuzz distributes tasks across 100,000 VMs. Each worker pulls a fuzz target, runs it for hours, then uploads any crashes back to the corpus. The cluster never sleeps. But the flood broke triage. Every crash needs reproduction, severity scoring, and routing to the right team. By March, Reports piled up faster than humans could validate them. The queue hit critical depth. Engineers spent more time triaging than fixing. So Google automated triage. The pipeline filters spam and duplicates, reproduces proof-of-concept exploits, assigns severity ratings based on impact, and routes reports to the correct subsystem team. It saves hundreds of hours per month. The results: 10 times more verified bugs per month, 90% reduction in false positives, and a median triage time under 12 hours instead of 3 days. Here's a triage report from the automated pipeline. Crash type: heap buffer overflow. Severity: high. Root cause: integer overflow in the JPEG decoder. Assigned team: Blink Graphics. Time to triage: 11 minutes. The automated system doesn't just triage crashes. It bisects commits to find the exact change that introduced the bug. It checks if the bug reproduces on stable, beta, and canary channels. It searches for duplicate reports across the entire corpus, all automatically. But here's the shift. Google's internal AI pipeline now discovers more routine bugs than the external crowdsourced bounty program. The balance flipped. In June, ClusterFuzz found 68% of all Chrome bugs. External bounties found 32%. Quote, Google's automated pipeline has functionally replaced the crowdsourced model for routine vulnerability discovery. Bounties still matter, but the game changed. Bounty hunters now target the bugs AI can't reach. 0 days requiring social engineering, logic flaws that span service boundaries, and vulnerabilities that need human creativity and context. The bottom tier belongs to the machines. Here's what that looks like in practice. AI fuzzing catches memory corruption, type confusion, and buffer overflows, bugs with clear signatures. Human hunters chase authentication bypasses, business logic errors, and cross-domain leaks, bugs that need understanding, not just coverage. Google's bounty payouts reflect the shift. The median payout for a ClusterFuzz eligible bug, memory corruption, use after free, dropped to $3,000. The median for a human-only bug, logic flaws, privilege escalation, rose to $15,000. The market adapted. The Chrome Vulnerability Reward Program started in 2010. For 14 years, it paid external researchers to find bugs. By 2026, the program still runs, but the majority of bugs now come from inside. The external model didn't die, it just handles the exceptions. The agent's impact shows up in coverage metrics. Pre-agent libFuzzer reached about 62% line coverage on Chrome's URL parser after 1 week of continuous fuzzing. Post-agent, the same target hit 79% coverage in under 8 hours. That 17-point jump unlocked entire subsystems, port validation, IPv6 handling, internationalized domain names, that random mutation barely touched. Quick recap. 1. ClusterFuzz runs 3 engines in Ensemble: libFuzzer, AFL++, Honggfuzz, sharing a global corpus and cloud storage. 2. A Gemini agent generates structured tests that hit narrow code paths by reading source and docs. 3. Automated triage filters, reproduces, scores, and routes crashes in hours instead of days. 4. The balance flipped. AI now finds 68% of Chrome bugs. External bounties find 32%. The pipeline keeps running 100,000 VMs 24/7 forever. The result? 1,072 bugs in 1 month. More than 2 years of manual work. And the pipeline keeps running 100,000 VMs 24/7 forever. The fuzzer never stops. The bugs never stop. And neither does the fix rate. If you enjoyed watching 100,000 robots find bugs faster than you ever will, subscribe. More Mechanism deep dives every week.